Hello, everyone. I'm a PhD candidate in physics at Missouri University of Science and Technology. I have completed all my research work here and currently looking for some opportunities. Today, I'm going to talk about fully differential study of post-collision interaction and the few body dynamics of simple atomic systems. Quantum mechanical few body problem is one of the fundamentally most important and yet unsolved problems in physics, where the essence of the few body problem is the Schrödinger equation is not analytically solvable for more than two mutually interacting particles, even when the underlying forces are precisely known. Dynamic few body systems like fragmentation processes are especially challenging. Atomic fragmentation processes are particularly suitable to study the few body dynamics because in atomic systems, underlying interaction is electromagnetic, which is essentially completely understood. Moreover, in atomic experiments, systems with small particle number can be selected in which kinematically complete experiments can be performed, which offers a very sensitive test to the theory. One of the most important fragmentation processes is the ionization of simple targets by ion impact, which is often treated perturbatively in theory. One of the perturbative methods is given by the Born series, in which the transition amplitude is expressed as a power series expansion of the interaction potential. Here, the first term gives single interaction, second term gives two interactions, and so on. The disadvantage of this method is this infinite power series expansion must be truncated after some terms. An alternative approach in perturbation theory is given by distorted wave methods. Here, higher order contributions are treated in the wave function of the final state. In this case, three-body system consisting of target, nucleus, target electron, and projectile is broken into three two-body systems. For each two-body system, continuum eigenstate is a Coulomb wave, and the total wave function is expressed as the product of these three Coulomb waves. The disadvantage of this three-body Coulomb wave function is it completely ignores correlations between particle pairs. Therefore, it is only accurate if one particle is far from other two. In perturbation theory, understanding the few body dynamics really means accurately describing the relative contributions of higher versus first order terms. One higher order mechanism that is particularly important is known as post-collision interaction, or PCI. In PCI, incoming projectile interacts with the target electron at least twice. In the first interaction, the projectile transfers sufficient energy to the electron to be ejected to the continuum. And in the second interaction, they attack each other towards the original beam direction. However, because of the momentum conservation, for this second interaction to happen, there must be another interaction with the target nucleus. And this target nucleus can interact either with the electron or the projectile. So these are the two interaction sequences that lead to PCI. It is well known that PCI maximizes for electron projectile velocity matching region, but there is no kinematically complete data available in this region. So the motivation of this work is to fill that gap. Here is our experimental setup. A collimated proton beam from the accelerator is crossed with very cold target beam from a supersonic jet. The recoil ions formed during the interaction are then collected by weak electric field in recoil ion momentum spectrometer and finally detected onto a two-dimensional position sensitive detector. The scattered projectiles after the interaction are charge analyzed by using switching magnet and then passed through energy analyzer and finally detected onto another position sensitive detector. These two detectors are put in coincidence with each other. Here we directly measure all the momentum components of recoil ion and scattered projectile, and then the momentum components of electrons are deduced by using momentum conservation laws. So this is a kinematically complete experiment. Now let's look at our results. As for our time limit, I'm presenting just a tiny subset of all the results we have for two different targets, helium and hydrogen. Fully differential cross-section as a function of electron ejection angle are plotted here for different fixed electron energies. For both of the targets, the plots on the middle represent the exact projectile electron velocity matching region, whereas on the top and bottom are for lower and above the velocity matching region. Now let's take a closer look at the exact velocity matching of hydrogen atom. Here a clear two peak structure is seen. The first peak, which is bigger at 0 degree, is known as forward peak and is the signature of host collision interaction. And the second peak, which is closer to the direction of the momentum transfer, is the binary peak. And here, for all the pictures, both the red and blue curves represent different versions of distorted wave approximations calculations carrying essentially the same physics. For lower and above the matching velocity, both of the theories represent the data well, but at the exact velocity matching region, there is a significant discrepancy not only between experiment and theory, but as well as between two theories. And similar kind of structures are observed in case of hydrogen as well. In addition to a strong forward peak in the electron angle dependence, another signature of PCI is a strong peak structure in the ejected electron energy dependence of fully differential cross-section. Here, fully differential cross-section as a function of electron energies are plotted for different projectile scattering angles. And these upright arrows represent the exact velocity matching region, and a strong peak structure is observed at exact velocity matching region. And similar structure is observed in case of helium as well. And here also quite significant discrepancy, not only between experiment and theory, but also between two similar theories are observed, which shows that the exact velocity matching region is very sensitive to the details of the underlying few body dynamics. Now the question is, what are the possible causes for discrepancies? In theory, projectile target interaction is not accurate because, as I described earlier, this 3C wave function is accurate only if at least one of the particle is far from other two, which is not the case in reality. And capture is not included, capture channel is not included accurately in the theory. And the projectiles are treated as fully coherent waves, but in reality, they are not fully coherent. Now, this discussion leads to the question that what type of theory is needed. So from our data, it is clear that perturbative approaches do not work well. So we need non-perturbative approaches with two center basis set, including bound states, to account for capture, and projectiles should be described by wave packet with finite coherence length. In conclusion, fully differential cross-section were measured for different targets where the ejected electron and the velocity of the projectile matches. In this region, a strong forward peak and a very strong peak were observed in the angular dependence and the energy dependence of fully differential procession. Large discrepancies have been observed not only between experiment and theory, but also between conceptually very similar theories, which indicates that few body dynamics is very sensitive at the velocity matching region, and our data indicates the limitation of perturbative models and need of non-perturbative approaches. Thank you.